Okay, so yeah, got it. Okay, so thanks everyone. Thank Noah for the invitation. I'm really excited to give that talk to you today. It was part of my PhD project that I finished about 3 years ago now. It involved a lot of people, some of them are listed here, including Carl Guillemette and Loïc Labrousse, who were the professor who initiated this project. And it was in close collaboration with the Quebec survey, as well as it was funded by the Gen2 project. So today we're going to talk about Paleoproterozoic tectonics. And for that, we're going to take an example that is in our backyard, northern Quebec and Labrador, which is the Southeastern Churchill province, which is part of the Trans-Hudson region. So as an introduction, and maybe you've seen this figure before. So the idea to that figure is basically to introduce the huge debate that has been standing for the past decades about when did plate tectonic initiated. So if we think about Archean tectonics, we can think about a hot and weak lithosphere. We think about, distributed thickening. We think about a certain geometry that was in dome and basin, for example, and that could be reflected in the style of the metamorphic PTT path with a certain shape and a certain magnitude. By opposition, if we go to what is more modern or actualistic, it is characterized by the presence of high pressure or ultra high pressure rocks that have been exhumed, the juxtaposition of contrasting metamorphic grades, a strong strain localization along, crustal to lithospheric truss faults, and so on. And this could also be reflected with a certain shape and a certain magnitude of the PT path, with, for example, isothermal decompression in that case. And in the middle of that, we don't know. Was it a transition? Was it a certain metamorphic style, tectonic style? When did that transition happen? For how long? What was the thermal condition on the crust? Still a lot of questions to be answered. One way to answer that is to look at the metamorphic record through time. So this is one of the famous compilation, I would say, that was published by Mike Brown and Tim Johnson, 2018. And if you look, so this is the age here on the x-axis, and those are the thermal gradients, and they can be divided in, let's say, two major parts. The blue dots are representing the low DT-DP gradients that are related to subduction zones. And in red, you have all the IT-DP thermal gradients that relates to orogenic hinterland. And if we look at that bimodal distribution, it seems to have initiated during the Paleoproterozoic. So, and this is one of the proxies that have been used to argue for the initiation of modern plate tectonic during the Paleoproterozoic. So we should use metamorphic rocks as proxies to retrieve tectonic processes through time. And we should put great attention on the Paleoproterozoic terrains, as well as Archean terrains, as well as modern terrains. But for today, we're going to talk about Paleoproterozoic terrains and take an example. Okay, so for that, we're going to move here in Canada, in the Trans-Hudson region. I'm pretty sure that everyone is familiar with that. So the Trans-Hudson region is a Paleoproterozoic region with the final collision estimated at 1.83, 1.80 billion years. It's basically composed of two major parts. So the first one is the superior craton, highlighted here, that represented the lower plate of the system. And then we have the Churchill upper plate, that is basically composed of an amalgamation of different cratonic blocks that were juxtaposed together, and then that finally collided during the final collision with the superior craton. Again, estimated at 1.83, 1.80 billion. The Transhudson orogen, it has been proposed by Marc Saintonge and others that is the equivalent or an analog to the Himalayan Tibet orogen. This argument is based on the shape, on the magnitude. So if we put the two different orogen at the same scale, it's basically what we obtain. And it was based on the relative timing of the different metamorphic episodes in the two upper plates in regards or comparing to the timing of the onset of collision. But it has limitations. First, how do we date the onset of collisions? How is it constrained? And second, how are the metamorphic event constraints? So those are still questions that should be assessed in the Transhudson and in the Himalayan orogen. It's been considered as a prototype of modern accretion erosion. And finally, there are still questions that were remaining and that still remains. For example, what are the thermal conditions in the Churchill upper plate? So in the different segments of the Churchill upper plate. Can we assess and quantify the metamorphic rates in the upper plate? I'm talking about, burial rates, exhumation rates, and so on. And so for that, today we're going to zoom in a part of the Transhudson that is called the Southeastern Churchill province. That is outcropping north of Quebec and Labrador, and that is probably the less known part, one of the less known parts of the THO. Okay, so let's zoom in. Okay, so this is a simplified geological map of the Southeastern Churchill province. So on the west here, you see the Superior Craton. On the east, we have the North Atlantic Craton. And in the middle of that, this is what we call the Southeastern Churchill province. This is composed of three major parts. The first one is the Tongat orogen, which basically is issued from the collision between a couple of blocks here and the North Atlantic Craton. On the west, we have the New Quebec orogen with the famous Labrador Trough, which is the passive margin on the Superior Craton here. And in the middle of that, we have what we call the core zone, which is basically composed of different Orchian to Paleoproterozoic crustal blocks that are bounded by crustal scale shear zones that define an anastomose pattern here, and that have different origins. Some of them are interpreted to have been rifted from the Superior Craton before the THO. Some of them are juvenile. I'm going to go back to the Mistini Road example in a couple of minutes. And some of them are different from the Superior Craton. And finally, in the middle of that, we have a huge batholith, a calcaline batholith, which is called the Depa batholith, that has been dated around 1.86, 1.80 billion. So this is basically the geological framework. If we look at the different tectonic models that have been proposed, so this one is issued from the last synthesis that has been published 20 years ago now. So we have a record of dike swarm at 2.1, 2.8 billion years, meaning that there was probably some crustal rifting at that time, but this is one of the only record we have. What happened then, we have no idea, a lot of question marks. What happened in the core zone? What happened along the margin of the North Atlantic Craton, where how many subduction zones do we put? What was the timing of the collision in the Tongat orogen? Poorly constrained. Was the margin of the North Atlantic Craton reworked during the Transhudson? This is another question. What were the metamorphic conditions in the Tongat orogen? Another question. And finally, can we date better the timing of the final accretion on the Superior Craton? So those are a lot of question marks. So this is one model. More recently, David Corrigan and co-author have proposed, based on the analogy with the Himalayan Tibet orogeny and the indenter tectonics. They propose a relative motion of the superior craton toward the northwest. Same for the North Atlantic craton. And so they interpret some extrusion toward the southeast of the entire southeastern Churchill province that they estimated from 1.9 to 1.8 billion years old. So that's another model. This is another example, a model that we are still working on. This is issued from the MSc thesis from Marc-Antoine Vanier, who worked with us at Université Laval. And Marc-Antoine put his focus on the aeromag data fieldwork quartzy axis along major shear zones that are bounded the different crystal blocks. And Marc-Antoine proposed that, based on his investigation, proposed that the anastomose pattern of the shear zone is reflecting some northeast-southwest bulk coaxial shortening. So it's a bit different from what has been proposed by David Corrigan, for example. So a couple of different models that needs to be tested. But we lack quantitative metamorphic data. And this was one of the leitmotif of my PhD project a couple of years ago. We need more metamorphic data to use them as proxies to retrieve the metamorphic style and tectonic style in that specific region of the THO. So for that, and again, in close collaboration with the Quebec Survey, we did extensive field work, and we had access to the new database they built in the past 10 years. And so we decided to select specific samples from supracrystal units along kind of a transect from the superior craton towards the North Atlantic craton. And this is what I'm going to present today. If we look at that in a cross-section, we try to sample the different blocks to assess the metamorphic timing and style. So when I talk about metamorphic style, I'm basically talking about a petrochronology approach. So it's an integrated approach. The main goal of that is to obtain a quantitative PTTD conditions to build PTTD path. And for that, we combine a lot of tools we have. Petrography, fieldwork. We combine that with thermobarometry and phase equilibrium modeling. We also look at the grain morphology and textures. And we involve different chronometers. Why is it important? So to illustrate that, and this is a figure that is from Taylor et al. in Litos. So if we follow, so this is pressure temperature window. And if we follow a classical, PT path, we expect the different chronometers to record a different part along the same PT path. So for example, garnet is expected to grow during an increase of pressure and temperature. Zircon and monazite are expected to dissolve when crossing the solidus. It's not always the case. And regrow again as the system cools and exhume. So this is why it's important to use or to involve different chronometers. And we couple that also to the trace element chemistry of these chronometers. So this is a full petrochronological approach that we use systematically along that west-east transect across the southeastern Churchill province. So everything that I'm going to present in the next slide is published, so you can access it online, and specifically that's a paper that got the mention. So yeah, just Google my name and you will find it online. Okay, so first we're going to start looking at a specific block within the entire region, and this block is the Mistini-Biro domain. Why is it important? First, this is the only block in the region that is almost only Paleoproterozoic. There is no Archean basement. It's purely Paleoproterozoic. It's heavily migmatized. On the field, this is how it looks like. Diatexite supracrustal sequences that have been brought at depth to the granulate facies, opaques, bearing assemblages, but that metamorphism was totally undated. So we're going to look first at that specific block. So we did our homework. We did petrography. We did some SEM MLM mapping to estimate the different model proportions of the different phases. We had a careful investigation on the textural relationships. So for example, this is just one example, but as you can see, this is garnet, and we have a symplectite of hornblende and plagioclaser on garnet that could relate to isothermal decompression. And we also look at the mineral chemistry. So for example, this is the calcium distribution in a garnet porphyroblast, and you can see that it was totally homogeneized at high temperature. So once you've done that, we've done some phase area modeling. So on the right side of that slide, I put two different samples. So this is sample 1, this is sample 2. They both come from the same block, the Mistinibiru domain. They are both metasedimentary rocks. And if you model in the PT space, you obtain conditions of reequilibration at 8 kilobars, 7 kilobars, and about 750 degrees Celsius. But because we're dealing with migmatites and these rocks are interpreted to have lost a lot of melt, we did imply the melt reintegration technique. You basically reintegrate artificially some melt in the system. The aim of that is to have an idea of what was the prograde conditions of the two protolith. So first, having an idea of what was the protolith, and second, what was the shape of the section in the subsoidist conditions. So this is what we did. We reintegrated about 6% of melt in that sample 1, and about 12% of melt in sample 2 until reaching the hydrated solids. The main difference, if you look carefully, is the location of the garnet in. So in that first sample, the garnet in is expected or modeled at relatively low pressure in subsoidist conditions. And in that second one, the garnet in is expected at higher pressure and higher temperature in suprasoidist conditions. I'm going to go back just in a few slides. This is important in our story. So we dated garnets. This is one of the geochronometers we dated. So those are the results for the two samples. We obtained two isochrones. We have a first age here at 2143. So you start to see that it's not Trans-Hudson, it's before the Trans-Hudson event. We have a second one at 2121-ish. And if we look at the distribution, so those are trace element maps done by laser ICP-MS, laser ablation ICP-MS. And if you look at the distribution of the lutetium, this is one of the examples, you can see that the lutetium is located, or the higher concentrations of the lutetium are located nearby the nucleation center. We interpret that as the result of Rayleigh fractionation. It also means that these garnet have likely preserved the growth zoning and the diffusion was limited. So we're basically dating the prograde metamorphism, and we're dating when the garnet regulated and grew. So if we go back to our PTT path, and we're going to start building them, in that first sample, we have garnet at 2140-ish in subsoidist conditions. And in that second sample, we have garnet at 2121 in suprasoidist conditions. What about monazite? So this is again one of the two samples. That one is pretty cool. We have two different populations of monazite. So in red, so this is the H, and this is the yttrium content. And if you look there, we have two monazite two different monozoic populations. The first one that is represented by the red dots, that is expected to be older than the garnet, and another one represented by the blue dots that is younger than the garnet. And as you can see, the yttrium content of the old one, older than the garnet, is higher in that population compared to that one. So it suggests that we have a control of the yttrium content on the monozoic by the garnet. If we look now at the heavy rare earth element content, we can see that the fractionation of the heavy rare earth element content is higher, the slope is higher in the retrograde monozoic, in that young population. So definitely garnet has a control on the yttrium and heavy rare earth content of monozoic. So if we go back to our quantitative PTT path, we have a first monocyte in the two different samples, the first monocyte population that grew before garnet. So in that case, 2145, and in that case, 2150-ish. And we have a second population of monocyte that we interpret as retrograde, in that case dated at 2070, and that case 2085 and 90. So two different samples, but pretty similar monocyte records. What about zircon? So the final geochronometer we used for these rocks were zircon. This is one of the two samples again. So in that case, you can see the distribution of the zircon grains. We have 4 different populations of zircons. If we look at their shape, we can see that they are pretty stubby, rounded. They are classical anatectic zircon. If we look at their trace element content, we can see that the heavy rare earth elements pattern is pretty flat. And again, those are different features that lead us to the interpretation that these are 4 anatectic zircon populations. So it was these 4 populations. So we interpret 4 different zircon population along the same PT path in suprasoidis conditions. And in that case, we have 2 zircon population at 2080-ish that we interpret as retrograde. So we have a full quantitative PTT path, and we can also start to give a rough estimation of the duration of the anatexy. So the implication for that first part I wanted to talk about today. First, we first dated the granulate facies at 2.1. So 2.1 it's not that usual in the Trans-Hudson, so it's pretty cool. We were able to estimate the duration of anatexis from 50 to 70 million years. So these rocks have been in suprasoidis conditions for a long time. The tectonic settings is poorly constrained at that time. We know that there was likely a plume that was located in that region. It's from Hansen Blicker 2010. So it might explain the high thermal conditions, but we still don't explain how these supracrustal sequences were buried at depth. It's still an open question. But what we know is that they were likely exhumed before 1987, because I think they contributed to the Hutte Sauvage group. This is the detrital record of the Hutte Sauvage group. It's just a small basin on top of that. And we can see a peak at 2080, and I think it's the Mistini Road that contributed to that. So we have a full metamorphic history. But an important part is that we don't have any trace of the Hudsonian event. We don't have anything dated at 1.9 to 1.8 billion years old. And we think it's due to a couple of different things. First, the restitic nature. So that granulate facies metamorphism that was dated at 2.1 produced really restitic rocks. So it's really hard to then remetamorphose restitic rocks. It was likely positioned as a supercrustal position. So maybe there was a decoupling between the crust and the mantle, and during the Trans-Hudson orogeny, that block just acted as a as a tiny block on top of the system. So now we're going to move on to another part of the Southeastern Churchill province. And we're going to move on in the Tonga Torogen. So again, the Tonga Torogen is located on the east. Again, the idea was to investigate a transect along that suture and go within the North Atlantic crater. So for example, those are the locations of two different samples. One is located in the Tectonic complex that is interpreted as the accretionary prism, and one is located in the margin of the North Atlantic crater. If we look at them on a schematic cross-section that I took from the Wardle's paper, this is how it looks like. Magmatized Tectonic complex, supracrustal garnet bearing, sometimes sillimanite, a little bit of biotite, sometimes orthopyroxene paragneiss. And this is what we sampled in the margin of the North Atlantic crater. It's a garnet-bearing gabbronorite. So again, the idea was to test. So first to try to date the timing of the continental collision, assess the duration of the anatexy, and test whether or not the margin of the North Atlantic crater was reworked during the transit sonology. And the answer is no. We dated garnet in the North Atlantic crater, and we obtained Archean ages. So it suggests first a metamorphic event at 2.56 billion years. Similar ages in zircon and monazite have been obtained in the Saglek block. And it suggests that it was not reworked during the Hudsonian orogeny, which is one of the first take-home message from our paper. So then we're going to move on to the second part, the Tectonic complex. Okay, again, the accretionary prism. So we dated garnet, and we obtained a nice age at 1885 plus or minus 12. If we look at the distribution of the lutetium, again, the lutetium is located, or the highest concentration of lutetium is located nearby the nucleation center, which brings that to Rayleigh fractionation. We think that diffusion was limited. From the literature, we know that these sequences followed hairpin PT path with maximum metamorphic conditions at 850 to 900 degrees C. And we interpret the garnet core as having grown in subsoilous conditions. Then we dated monazites, and we obtain an age at 1873 that we attribute to the breakdown of apatite as soon as the rock crossed the solidus. Why we think that? We have chemical and textural relationships. I'm going to show you first textural relationships. So this is a micro XRF maps that I've put it in false color. The idea was to highlight the location of the apatite in green and the monazite in pink. And as you can see, we have different apatite grains. First grain here, the second grain here. So the apatites are located within the garnet cores, and that's it. By opposition, the monazite are located always in the garnet rim or in the matrix. So we think that the garnet core grew in the presence of apatite in subsoilous conditions and continue to grow after the apatite broke down to produce monazite in peritectic conditions. Finally, we dated zircon that we interpret as retrograde, coeval with the melt crystallization, estimated at 1848 plus or minus 12. So again, a full PTTT evolution of the Tectonic complex. So what are the implications? So first, we can use the garnet or the garnet chronometer as a proxy to date the onset of the continental collision and the burial of the supracrustal sequences at depth. And we have a constraint at 1885. We have textural and chemical evidences of prograde peritectic monazite that were entrapped in the the garnet rim, and we were able to estimate the duration of the anatexis of about 20 to 40 million years of anatexis. If we look, so it was the two samples we just look at were these ones. And if we look at the samples that were selected in that part of the core zone, this is the work from Benoit Charette, who did the master thesis with Carl Guillemette. And we obtained the same age. We have garnet growing in all these blocks at 1885, 1890. So this is what we attribute to the timing of the collision. This is followed by a long period of anatexis, about 50 million years. So everything was kept at middle crust level for a long time. And then the cooling was co-evolved for all these blocks. So from that time, this block acted just as one stiff block in the system. Finally, we're going to move to the western part of the Southeastern Churchill province. This is represented by the New Quebec region. This one is maybe more famous, Labrador Trough, the passive margin. Then we have the Rachel-Laporte zone, which is the fallen basin deposited on top of the upper plate. The upper plate is represented by the Kudjak domain. And if we look at the schematic cross-section, again, superior craton, the lower plate, passive margin, Labrador Trough, fallen basin, Rachel-Laporte zone, and upper plate, Kudjak domain, plus the rest of the core zone that was already accreted. I would like to emphasize that when you go on the field, it appears to be an apparent continuous Barrovian sequence with the operation of biotite, then garnet, then storolite, kyanite, and so on, without any breaks. You cannot really recognize any breaks. I'm going to demonstrate in a couple of minutes that there is a break actually, and it's not a continuous sequence. So we decided to select a couple of samples to do the full quantitative petrochronological approach. Oh yeah, so I've been talking about garnets, but this is a nice picture from the field. This is an amphibolite layer with garnet that is hosted in the paragneiss that is migmatized. And one fun fact about that this specific garnet porphyroblast, if we zoom in and we look how they look like under a microscope, we can see the garnet porphyroblasts, and then a nice textures with a symplectite of plagioclase and orthopyroxene that we interpret as the result of isothermal decompression. Yeah, just to show you a couple of geologists, so we like to see rocks. Okay, so let's go back to our quantitative PTT path. So the first record we have is in the Kudjak domain. So in the Kudjak domain at about 1835 million years, we were growing garnet. The rocks were growing garnet and were buried at about 10 kilobars. So this is the first record we have in that specific region of the Southeastern Churchill province. The next record is at about 1805. At that time, we had first deposited the fallen basin, the Rachel-Laporte zone. We were exhuming the supracrustal sequences from the Kudjak domain. We have Zycon that we interpret as retrograde that followed isothermal decompression, like I just said, in the Kudjak domain. And it was co-evolved to the burial of the supracrustal sequences of the Rachel-Laporte zone. So at the same time, we were exhuming that block and burying that block. So it implies that we need a tectonometamorphic discontinuity at along the what we call the Lac-Turcotte fault. And finally, we have rutile that we interpret as the cooling of the system. And everything was exhumed together alongside with the development of the fold and thrust belt in the Labrador Trough. So again, it's not because on the field we have an apparent Barrovian sequence that it's a true Barrovian sequence. Actually, it is separated by a true tectonometamorphic discontinuity. and the timing of the burial of the supercrystal sequences record the lack of about 30 million years in this specific region. Okay, so it's time to wrap up. So we have a tectonometamorphic evolution of the Southeastern Churchill province with about 100 million years of crustal assembly. So if we wrap up a bit and we look at the evolution, so first, the first metamorphic record we have is in the Tonga orogen. So I don't mention, sorry, I forgot to mention. So I'm not talking about anymore about the Mist-Nibi domain, MRD here. It didn't record any of the Trans-Hudson orogen. So for the Trans-Hudson orogen, the first record we have is the collision of the Tonga orogen, which is estimated from Godet at 1895, 1885. It's the collision between these blocks and the North Atlantic crater. After that, we interpret that they acted as a stiff block during the rest of the orogeny. The second record we have is the burial of the Kuujjuaq domain at 1835. It's also the timing of the end of the anatexy in the rest of the region. So all these blocks were in anatexis from the initial collision, 1885 to about 1840. We think that Lac Tudor shear zone is a boundary. Okay. We can start to see that the diachronicity of the evolution toward the west of the metamorphic record that started on the east and moved to the west, building or creating the upper plate, the Churchill upper plate. And the final metamorphic record we have is estimated at 1805. This is the final collision on top of the superior craton, development of the Fallen Thrust Belt, burial of the supracrustal sequences of the Fallen Basin here, and a metamorphic discontinuity. So again, I like to highlight the fact that it's diachronous. The metamorphic record along or across the Southeastern Churchill province is diachronous. Yeah. So the take-home message for you guys today. So first, we did a quantitative PTTD approach by using different chronometers, coupling with trace element chemistry, textural relationships, so petrochronology. We're able to develop or test the tectonic models. So we think that this part of the Trans-Hudson did build as successive accretions of coastal blocks that started with the Tonga orogen at 1890 and that finished at 1805 on the superior craton. We're able to show that it's a diachronous metamorphic record of the growing Churchill upper plate from east to west. We're able to point the different boundaries in that specific part of the THO. And please be careful with the apparent continuous metamorphic gradients. They need to be revisited, in my opinion, by using a quantitative metamorphic approach. Finally, this is not what we are dealing with high-grade terrains, or this is heavily metamorphosed terrains. We can use different different chronometers. And so, for example, and from my experience, garnet has a strong potential to preserve grout building. And zircon and monazite dating in migmatite, it's not straightforward. Sometimes it records different population, prograde, retrograde, so it needs to be coupled with trace element chemistry, textural relationships, and so on, to be sure what the interpretation of the obtained age are. So back to the initial question, and this is my final slide. Is it an example of Paleoproterozoic tectonics? So first we have new dots. As you can see, we don't have low DT, DP gradients. So it's pretty high temperature conditions. So the lithosphere was quite hot. We have no evidence of HP, so it's in French, HP low-T gradients, so no evidence of that, no ultra-high pressure rocks neither. We don't have any evidence of oceanic lithosphere, or we don't have any ophiolite at that time during the Trossardsen. We interpret, and this is one of the interpretations, we interpret that a coaxial shortening was accommodated by a network of anastomose shear zones, at least on the eastern part of the Southeastern Churchill province. We have evidence of strain localization, we have evidence of isothermal decompression, we have evidence of a folded thrust belt, so it is more attributed to a colder lithosphere in the New Quebec orogen. So it's a bit different. And we have evidence of crest mantle decoupling. So I think we have a bit of what we call primitive tectonic features, and we have a bit of modern plate tectonic features. So we might be, it might evidence some sort of Paleoproterozoic tectonics with its own geological features, I would say. Thank you for your attention.